My name is Joachim Grevel. I'm delighted to be invited to give you this tutorial on the application of survival analysis to the assessment of multi-state models in clinical data analysis at this virtual page meeting. I would like to start with a comparison of time-to-event analysis methods with which you may be familiar and introduce a new method to you. There's the Cox proportional hazard model, which allows us to calculate the hazard ratio for relative risk for active treatment versus placebo, often used in progression-free survival and overall survival analysis. There is also a parametric version of the Cox proportional hazard model, which allows us, in addition, to simulate the treatment effect and to perform exposure response analysis. There's the fine-gray proportional hazard model, which will take dropout as a competing risk when calculating the hazard ratio of the absolute risk of an event occurring. And today we will focus on a new methodology, the semi-Markov multi-state model. Each of the methods to do time-to-event analysis has its shortcomings. The Cox proportional hazard model, as well as its parametric version, both are treating competing risks as right-censored events. The fine-gray proportional hazard model is creating an unnatural risk set when absorbing states are in the competing risks. The semi-Markov multi-state model builds far more complex models and requires larger data sets. We are now going through the exercise of dividing a phase 3 clinical study in oncology into various states of interest. We follow a patient as he starts by randomization to a specific treatment arm. He enters the initial state. From there he has options to go into various transient states, for example progressive disease or discontinuation due to adverse events. He may be lost to follow-up and enter thus an absorbing state. He may also die as well an absorbing state. At any time, administrative data cutoff may cut short an individual data set. This is not treated as a state, but as right censoring. In the following 3 slides, I show you cartoons of the methods used to analyze time-to-event data. Here we see the Cox proportional hazard model or its parametric version. For example, we may analyze a single transition with this method from start to progressive disease. In this case, all other events are used as right censoring, together with the legitimate event for right censoring, the administrative data cutoff. Therefore, we have a mixed bag in right censoring consisting of transient and absorbing states which have really nothing to do with right censoring per se. The same applies, of course, when we use the method to analyze overall survival data. Here the cartoon for the fine gray proportional hazard model. We see that the method is improved to the degree that right censoring is really only using the administrative data cutoff, and that we have an event of interest, in the current slide here, progressive disease, and we have a competing event. In this case, it's a mixed bag of either absorbing states or transient state, which is a problem for this type of analysis. If instead we do justice to each state by placing it into a multi-state model with semi-Markov processes, we can build a realistic model which gives correct answers to all stakeholders in drug development in oncology: the developer, the regulator, the patient, the clinician, and the payer. In the current cartoon, each state is in its proper place and all competing transitions of interest are defined. Furthermore, right censoring is reserved for administrative data cutoff. I now take the liberty to simplify the multi-state model, not in order to facilitate model building and parameter estimation. Complex multi-state models can be reliably analyzed with the current packages at offer in R, but in order to guide you in the tutorial through an exercise which comprises of all the methods you need to arrive at unbiased conclusions. The starting state is the diagnosis. There is a transient state, relapse of disease, and we have two absorbing states, death and dropout. All competing exit transitions from diagnosis and relapse are in place. To analyze all events and transitions in such a multi-state model, we have two approaches which are equivalent and can be transformed into each other. Both approaches describe all transitions as a semi-Markov process. Focusing on approach 1, we have formulated transition probabilities and sojourn time hazard functions. Probabilities give us the direction of transitions, the hazard functions give us the rate. We can incorporate covariates. We are able to formulate the entire model in a full parametric form. We are thus able to simulate data. We have, however, a large computational expense. For the quality of fit, we can generate parametric and non-parametric displays such as cumulative incidence functions, and all our estimates, both numerical and graphical, can be produced with 95% confidence intervals. Approach 2 is somehow simpler, as it formulates only intensity transition functions which incorporate both the direction and the rate of the transitions. We again can incorporate covariates. We can build the model in full parametric form and thus simulate data. We have a moderate computational expense in comparison to approach 1. We have our ways of showing goodness of fit and the quality of our model through parametric and non-parametric displays. And again, we can have 95% confidence intervals for all our numerical and graphical displays. Here I introduce you to the notation of the functions used in approach 1 and approach 2. The upper one is the sojourn time hazard function, which shows us the immediate hazard of leaving the current state I for a future state j. The second, the intensity transition function, shows not only the rate of the transition but also indicates the specific state into which this transition will enter. I will also use a simple dichotomous covariate in our functions, which is multiplied with an exponent. It's notated as z, has the values 0 and 1. 0 stands for placebo, 1 for active treatment, and we are estimating the parameter beta for the covariate influence. To simulate a data set for our chosen model, we use Weibull-like functions for the intensity transition functions. For each of the 5 transitions, each Weibull function has 3 parameters: the A parameter for shape, the B parameter for scale, and the beta parameter to exemplify the covariate influence. Let me pick the parameter beta 1, 2. That is the exponent of the influence of treatment on the transition from diagnosis to relapse. The parameter being negative means that under active treatment that transition is impeded. We simulate from the chosen model by adopting an algorithm developed by Beiersman. For each of the patients we simulate first an event time from the survival function of the holding time in the current state. Then, second, through a multinomial experiment, we decide which state the transition is reaching. Finally, third, we repeat steps 1 and 2 until an absorbing state is reached or until the patient dataset is truncated by right censoring. Here I show the transition events and the number of patients caught by right censoring of one of the simulated studies. Of 1,000 patients starting in the state 1 diagnosis, 159 have relapse, 220 die, and 500 drop out. Of the 159 patients reaching the transient state of relapse, 84 progress to death and 5 drop out. In total, 121 patients are caught by right censoring in state 1 and 70 patients are caught in state 2. We now estimate the parameters of our multi-state model for our simulated study. The methods for optimizing the likelihood are described in backup slides. The current slide and the following 4 slides show graphically the transitions of our multi-state model. Here first we see the transition from diagnosis to relapse described as a cumulative intensity transition function, and at the bottom a cumulative incidence function. In each case we see the non-parametric representation of the transitions in red, and in black we see the parametric transitions functions either for the active treatment as a dashed line or for placebo as a solid line. Under active treatment, it is clear that the transitions to relapse are being slowed down. The same applies to the transitions from diagnosis to death. Again, with active treatment, the rate of increase of the transitions with time is decreased for active treatment. A very different story is seen for the transitions from diagnosis to dropout. There it happens that the transitions are accelerated for active treatment and slowed down for placebo. There is barely any difference in the transition from relapse to death whether patients are on active treatment or placebo. And transitions from relapse to dropout are altogether rare and really too few to estimate the influence of active treatment or placebo. On this slide, I show you the parameter estimates for our chosen base model first. We have for all 5 transitions chosen Weibull type intensity transition functions. We see the estimated parameters on the left and can compare them to the true values used in the simulation on the right, and we see very good agreement between estimated and true values. Now we expand our model and include covariate influences. How the parameters change by the inclusion of covariate influences can be appreciated by comparing on the left side the parameters of our multi-state model in the absence of covariates, and on the right side in the presence of covariates. and we can compare the value of the log likelihood between the base model without covariates and the full covariate model. In this and the following 4 slides, we enrich our goodness of fit evaluation through 95% confidence intervals. Here on this slide, we see the transition from diagnosis to relapse. We see a clear separation between active treatment and placebo, and active treatment seems to slow down the progression to relapse. The same applies to the transition from diagnosis to death. Again, active treatment and placebo well separated, and active treatment slowing down the transition to death. Very prominent is the transition from diagnosis to dropout. It is reversed. Active treatment is accelerating transition to dropout, and the active treatment and placebo again well separated. From relapse to death, we have no separation between the 2 treatments, and it is very hard to decide that there is any influence on death after patients have progressed to relapse. And finally, on the transition from relapse to dropout, it is very clear that there are simply too few events happening to draw any inference. To estimate the influence of treatment on the 5 transitions in our multi-state model is of interest to the developer of the treatment, but is also a prerequisite for answering the key question of interest to the patient. Practically speaking, will I stay event-free while I'm on active treatment? Or mathematically speaking, is the sojourn time in the initial state longer when the patient is on active treatment? We now apply a hypothesis test on the survival function of the holding time in state 1. Our null hypothesis and alternative hypothesis are formulated here, and we can show that at any fixed time point, the null hypothesis that survival is equal for both treatment arms can be rejected. When we do the math for this hypothesis test, we apply the so-called delta method. We can show at a reasonably low significance level that patients on active treatment leave the starting state, the diagnosis, faster than patients on placebo. While the standard Cox proportional hazard model shows a hazard ratio of 0.38 with 95% confidence intervals from 0.27 to 0.56, demonstrating that active treatment slows the transition from diagnosis to relapse. Yet, this happy effect only applies to a minority of patients, those not dropping out. I am convinced that in the future regulators want to see both types of analysis done in phase 3 trials in oncology, the Cox proportional hazard model and the full parametric semi-Markov multi-state model, tailored to the specific structure of the study in question. Because the survival functions of the holding time in a desirable state directly reflect patient benefit. In our current example, this type of survival is shorter for patients on active treatment. At the end of my tutorial, I want to give special thanks to the tireless work of my graduate student A. Harris Jameel and to his academic advisors at the University of Nottingham, Drs. Bignell and Fallaize and Dr. Stupfler at the École des statistiques et des analyses des informations à Paris. I also give special thanks to my colleague and friend Pleasant Chaco at BAST.